Well, we're in section 3.2 having to do with general solutions for linear equations. And linear equations really means linear differential equations. So if a differential equation has solutions y1, y2, y3, all the way up to yn, somehow I found them, and by the end of this chapter we'll know how I'm going to do that, then there is a general solution. General solution. And basically we're using English is what we're trying to do here. So that solution is going to be y of x is equal to c1y1 plus c2y2 plus blah 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 cnyn, all of them where the c's are constants of integration that we get from our initial conditions if we have them. And the cool thing is that these things are going to be exist. They will exist. Otherwise, we couldn't have the class. And they're going to be unique. So that also makes it easy for me to grade things. Okay, first thing we're going to look at is the Wronskian of the solutions. Now we're going to use the Wronskian of the solutions in a way to solve these differential equations later, and so that's why we're discussing them now. So the Wronskian of y1, y2 up to yn, if that Wronskian is 0 on some interval, I, so it doesn't have to be on the whole number line, it can be on some small portion of the number line, then the solutions are linearly independent. If that Wronskian is not equal to 0 on some interval I, then I'm not linearly independent, and my solution should be linearly independent is the bottom line of things. When we move to theorem 4, we find general solutions to homogeneous equations. Okay, well, if I could spell homogeneous. And homogeneous equations mean that I've got some equation and it's equal to 0. So I've got y to the nth derivative plus some function of x only, y to the n minus 1 derivative plus blah 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 p n minus 1 x y first derivative plus pnx y is equal to 0. If I have my function y and all the derivatives of y added together and I'm equal to 0, then my equation is homogeneous. And there is going to be a solution for this homogeneous equation on an open interval. And for our purposes, we never care about that interval, so that's perfectly okay too. The PI's have to be continuous. Need to be continuous. So, we could say, well, P1x is equal to 0 and 1 for x is equal to, or greater than 50, and x is greater than 50, it's going to be 1. Well, that's not, if our interval included that, we're not continuous there, so that I wouldn't have a solution there. And when I get done, I'm going to have a solution y of x, and it's going to be c1 y1x plus c2 y2x plus cn, all the way out to cn y and x. So that's what my solution is going to look like. Now, how we get there, that's a different issue, and by the end of the chapter we should have that figured out too. Now, when I have a non-homogeneous equation, differential equation, what I have is something that isn't equal to 0. So I've got yn plus p1x yn minus 1. That's the nth derivative, n minus 1 derivative, plus pn minus 1 x y1 plus pny is equal to some function, f of x. And we call that a forcing function, and that's why we put an f there, call it forcing. So when I have that situation, what I do is I solve the homogeneous equation first. And you say, well, there isn't one. If I could spell homogeneous equation first. So we take the equation and we make it equal to 0, and we solve it. And we call that solution y sub c. C is complementary, so, but I normally don't use that word. I just call it y sub c. And then we find the particular solution. Find the particular solution. And again, we're not, in this section, we don't tell you how to do that, y sub p. And then for your final answer, y of x is going to equal y sub c plus y sub p, whatever they are. And then at that point, you still have to apply initial conditions to get the constants of integration out of there. So this is final answer minus 1. And then when you get the final answer, you have applied the initial conditions. Okay. Okay, we're going to do some homework problems now. I'm going to start with number 2. And we're going to read what it says to do. Problems 1 through 6. Show directly that the given functions are linearly dependent on the real line. That is, find a non-trivial linear combination of the given functions that vanishes identically. Okay, so that's what we're going to do. We're going to start with problem number 2. And what do we have? We have f of x is 5, g of x is 2 minus 3x squared, and h of x is 10 plus 15x squared. So what we want to do is we want to find something that says a f of x plus b g of x plus c h of x is 0. So that's what we're supposed to do. So I've got 5a plus 2b minus 3b x squared plus 10c plus 15c x squared. I want that to be 0. And I have to find a, b, and c. Well, if I look at the unit term, what do I see? I see that 5a plus 2b plus 10c has to be 0. And if I look at the x squared, if I look at the x term, I see nothing because I have no x's. If I look at the x squared term, I find that minus 3b plus 15c has to be 0. And now I look at that and I say, isn't this lovely? I have two equations and 3 unknowns. What is that going to do for me? And I say, well, who knows? We'll find out, won't we? Okay, so what I'm going to do is use my calculator, and I'm going to put these 2 equations in my 3 unknowns part of the calculator. So I'm going to put in that equation, I'm going to put in this equation, and for the third equation, I'm going to leave it all zeros. And I'm going to hope my calculator does something. So I do that, and I get that the A guy is minus 4z, and the B guy is 5z. In the C guy, I have z equals z for the C guy. And really I have, for the A guy, I have x is equal to, I'll do that again, because that's not overly clear what I'm doing. Okay, so my calculator is saying that the x guy is x is equal to minus 4z. And the y guy, y is equal to 5z. And the z guy says z is equal to z, but that really is 1 times z if I look at it that way. Okay, so I'm going to do something cool. What is it? I don't know. We'll find out. So we're going to say x, that this means A is going to be minus 4, and B is going to be 5, and C is going to be 1. That's how we're going to interpret those numbers coming in there. Okay, so if that's the case, is minus 4 times 5 plus 5 times 2 minus 3x squared plus 1 times 10 plus 15x squared, is that 0? That's if it is, then we're all set. Okay, so I got minus 20 plus 10 plus another 10. That's convenient. I have minus 15x squared. I've got plus 15x squared. In equal to 0. Check. Okay, so I have found a linear combination that I can come up with, and it's going to be 0. Isn't that nice? So we're going to do it one more time with problem number 4. Okay, and what we have is f of x is 17, g of x is 2 sine squared x, and h of x is 3 cosine squared x. Okay, so what I want is something that is 17a plus b times 2 sine squared x plus c 3 cosine squared x, and that has to be 0. Okay, well, I've got this thing in here that's sine squared x plus cosine squared x is equal to 1 sitting here. So if I can get the b's and the c's so that they end up giving me a number that is the same. So I want 2b to equal 3c. Okay, I want that to be the case. And I also want to be the case that when I take 2b, okay, so they're equal. Okay, so 2b has to equal 17a. Okay, so that has to be the case too. So how are we going to do that? Again, we have 2 equations, 3 unknowns. So I got 17a minus 2b is equal to 0, and I have 2b minus 3c is equal to 0, and I have 0, 0, 0. I'm going to put in 0, 0, 0 on the other third. So I have 3 equations, 2 equations, 3 unknowns. Okay, so I'm going to put that in my calculator and see what that gives me. And that gives me that x, which is the a guy, is going to be 6 over 17 z, and y, which is the b guy, is 3 over 2 z, which we knew, and z is equal to z, and that sort of makes things interesting. So, okay. So if we make a, I'm going to make a 6. A is 6. So if a is 6, 17 times 6 is how much? I should be able to do that in my head, but I'm not going to. Quit out of my calculator. 17 times 6 is 102. 102. Alright, so that means that 2b has to be 102. B is 51. Or is it minus 51? B is 51 in order to make it minus there. Okay. Okay, so we're going to go with minus 51. And 3c has to be, this has to be minus 102, minus 102. So c is going to be minus 34. And other than magic, we end up with 6 times 17 plus minus 51, 2 sine squared x plus a minus 34, 3 cosine squared x becomes 0, and we see that on the real interval, this guy is not linearly independent because I found a point where he wasn't. Now it's just a matter of how much did I cheat to do that. Okay, we're going to do number 8. Use the Rodskin to prove that the given functions are linearly independent. Okay, so we want to prove that f of x e to the x, g of x e to the 2x, h of x e to the 3x on the real line. Okay, so we're going to look at that Wronskian. Okay. Alright, so the Wronskian's equal to e to the x, e to the x, e to the x. Isn't that wonderful? E to the 2x, 2e to the 2x, 4e to the 2x, e to the 3x, 3e to the 3x, 9e to the 3x. Alright. So, 18 e to the 6x plus 3 times 1 times 1 is 3 e to the 3, 4, 5, 6x. 4 e to the 6x minus, going the other way, 2e to the 6x plus 12 e to the 6x plus 9 e to the 6x. Alright, 18, 22, 25. 25 e to the 6x minus 12, 14, 14 and 9, 14 and 9, 23 e to the 6x is equal to 2 e to the 6x. Now, on the real line, is 2e to the 6x ever equal to 0? Ever not, is it ever equal to 0? And the answer is no, it isn't, because it's something that looks like this. And it never crosses the 0 thing. So this is not equal to 0, therefore these guys are linearly independent. Right. Well, at least that wasn't as silly as the other guy was. Okay. Going to do number 14 next. Okay. We have a third order homogeneous linear equation and 3 independent solutions. Find the particular solution satisfying the given initial conditions. Okay, so that should be easily enough done. 14. The third derivative, minus 6y double prime, 11y prime, minus 6y is equal to 0. Have initial conditions, y at 0, 0, y prime at 0, 0, y double prime at 0, 3. Okay, that's all we need. And we have y1 is e to the x, y2 e to the 2x, y3 e to the 3x. I think I've seen that solution before, haven't I? Yeah, the guy we just worked. Okay, well, that being the case, y is going to be c1 e to the x plus c2 e to the 2x plus c3 e to the 3x. applying the first initial condition, y prime at 0 is 0, implies c1 plus c2 plus c3 are 0. And it'd be nice if I made that c2 a little better, a little more of a c. Okay. Now we're going to look at the first derivative, c1 e to the x plus 2 c2 e to the 2x plus 3c3 e to the 3x. And we find that y prime at 0 is 0. And we have that's going to be c1 plus 2c2 plus 3c3. And then we go and look at the next derivative, y double prime of x. And we have c1 e to the x plus 4 c2 e to the x plus 9 c3 e to the x. And we look at y double prime at 0, and we get 3. So 3 is equal to c1 plus 4 c2 plus 9 c3. So now we have 3 equations, 3 unknown. Thank you very much, author, for giving us such an easy problem. Okay, so c1, c2, c3 plus 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 is equal to 0. And c1 plus 2, c2 plus 3, c3 is equal to 0. And c1 plus 4, c2 plus 9, c3 is equal to 3. And a normal person with 3 equations, 3 unknowns, would just use their calculator and write down the answer. But I'm not normal, so we'll use Kramers rule and see if we can get it wrong. Okay, so C1 0 0 3 1 2 4 1 3 9, and on the bottom we have 1 1 1 1 2 4 1 3 9. Okay, looking good. 0 9 0 minus 6 0 0. On the bottom, what do I have? I have 18. I have 3. I have 4 minus 2, 12, 9. Okay, and all things being done, I have 3 over 2. So 3 over 2 is my C1. And now I'm going to look for C2. I know on the bottom I have 2, so I'm going to keep it 1 1 1 0 0 3 1 3 9. And I'm going to have 3 minus 9 divided by 2, also known as 3, also known as minus 3. And if I know C1 and C2, I better be able to find C3, right? So C1 plus C2 plus C3 has to be 0. So if I have 3 over 2 minus 3 plus C3 is 0, then C3 had better be 3 over 2. Okay? So unchecked final answer y of x is equal to 3 over 2 e to the x minus 3 e to the 2x plus 3 over 2 e to the 3x. And now that keys us to check our final answer. So checking y is equal to 3 over 2 minus 3 plus 3 over 2 y prime. Well, we should check the initial conditions also. So y at 0 is supposed to be 0. It is 0, check. All right, y prime. 3 over 2 e to the x minus 6 e to the 2x plus 9 over 2 e to the 3x. Y prime at 0 is supposed to be 0. What is it? It's 9 halves. It's 12 halves, which is 6. Minus 6 is 0. Check. Y double prime is 3 over 2 e to the x, 12 minus 12 e to the 2x, plus 27 over 2 e to the 3x. Y double prime at 0 is supposed to be what? Y double prime at 0. This is 14. It's supposed to be 3. Alright, so I've got 30 divided by 2 is 15, minus 12 is 3. That checks. Y double prime, triple prime, is 3 over 2x minus 24 e to the 2x plus 81 over 2 e to the 3x. Okay, now can I see all of those at the same time? Almost. I can almost see all of them at the same time. Alright, so I'm supposed to have minus 6 of these guys and plus 11 of those guys and minus 6 of them and 1 of these guys, and when I get done I'm supposed to be 0. Okay, well, I can't really see everything at the same time, so I'll do my best. Alright, so what we'll do is we'll put these guys in my calculator one at a time, see what we get. Okay, so minus 6 times 3 over 2 plus 11 times 3 over 2 minus 6 times 3 over 2. And what's the last guy? Plus 3 over 2 equals 0. Okay, so the first row is 0. Second row, second column. Okay, minus 6, that'd be 18. So I got 18 minus 66 plus 12 times 6 minus 24, and that's 0, 2. Excellent. Plus next row, okay, so I got minus 6 times 3 over 2 plus 11 times 9 over 2 minus 6 times 27 over 2, and the last guy is what? 81 over 2 plus 81 over 2, and that comes out to minus 99, so I probably did something wrong. So first thing we'll do is 3 times that, 3 times, okay, so we're going to do it one more time. Well, I can look at my calculator and, well, maybe I can. Minus 6 times 3 over 2 plus 11. Oh, last time I put in minus 11, that's the problem, times 9 over 2 minus 6 times 27 over 2, and the last guy is 81 plus 81 over 2, 0. Okay, so all three rows are 0. The problem checks. We have the right answer. Isn't that convenient? Next one is problem 16. There's our problem number 16. And this looks like a similar type of thing. So we have third derivative minus 5y double prime plus 8y prime minus 4y is 0. I have initial conditions. Y of 0 is 1. Y prime at 0 is 4. Y double prime at 0 is 0. I have y1 e to the x, y2. It's the same answer, same problem. E to the 2x, y3 e to the 3x. No, it isn't. X e to the 2x. Different problem. Yeah, let's see if I can do that better. Y3 is x e to the 2x. Now, so rechecking the problem, making sure I have it written down right. Otherwise, things will not turn out good. Okay, so that looks halfway decent. Alright, so that being the case, we can write our general solution. Y is equal to c1 e to the x plus c2 e to the 2x plus c3x e to the 2x. Applying the initial condition, y at 0 is equal to 1, which is going to be c1 plus c2. Because when x is 0, that guy goes away. Okay. Y prime x. c1 e to the x to c2 e to the 2x plus c3 e to the 2x plus 2 c3x e to the 2x. Y prime at 0 is supposed to be 4, which is going to be c1 plus 2c2 plus c3, because at 0 that term goes away. Okay, one more. Y double prime at x. c1 e to the x plus 4c2e to the x, 2x, plus c3, 2c3 e to the 2x, plus 2c3 e to the 2x, plus 4c3x e to the 2x. So rewriting that, combining like terms, c1 e to the x, 4c2 e to the 2x, 4c3 e to the 2x, plus 4c3x e to the 2x. And y double prime at 0 is supposed to be 0, which is going to be c1 plus c2, 4c2, plus 4c3. So now I have three equations, three unknowns. All I have to do is remember what they are. Okay, so c1 plus c2 is equal to 0. No, it's not. Is equal to 1. C1 plus 2, C2 plus C3 is equal to 4. Is equal to 4. And C1 plus 4, C2 plus 4, C3 is equal to 0. Okay, so now we're all set. I'm going to do Kramers rule again. C1 is going to be 1, 4, 0, 1, 2, 4, 0, 1, 4, and on the bottom I have 1, 1, 1, 1, 2, 4, 0, 1, 4. And so we'll look at the bottom guy first. I have an 8. I have a 1. And I minus, there's a 0, there's a 4, there's another 4, so that's an 8. So the bottom's going to be a 1. On the top, I have an 8. I've got a 0, I got another 0, I got another 0. I got a minus 4, minus a minus. That's 0. That's a 4. That's a 16. So for C1, for C1, I get a 1 on the bottom, and I get a minus 12 on the top. So C1 is going to be minus 12. Well, if C1's minus 12, then C2 had better be plus 12. C2 is plus 12. And if that's the case, then C3 had better be what? Well, let's think. What should C3 be? Okay, so if I got minus 12 plus 12 plus 4 times 12. 4 times 12, well, I'm looking at the third equation. Okay, so I've got minus 12, I got 4 times 12 plus 4 times C3 is supposed to be equal to 0. Okay, so I have 36 plus 4c3 is 0. I have c3 is minus 9. Minus 9? Yeah, okay. Sorry about that, guys. If C1 is minus 12, then C2 is 13. Way to go, instructor. C2 is 13. And if C2 is 13, then minus 12 plus 4 times 13 plus 4 times C3 is supposed to be 4. It is. It's supposed to be 0. It's supposed to be 0. Okay, so 4 times 13 is 52. 52 minus 12 is 40. So C3 is 40 divided by 4, which is 10. Okay, very good. So final answer, y of x is minus 12 e to the x plus 13 e to the 2x plus 10 x e to the 2x. Minus 40 minus 10 minus 10 x e to the 2x. Okay, much better. Now we got to check our work. Do we have to check our work, or can we look in the back of the book? I think we can look in the back of the book. Number 16 is there. And we have minus 12 e to the x plus 13 2x 10. Yeah. So checking by back of book. Boom. Checked. All right. Do we do another one? Yes, we do. One more. Seeing that you guys get to go to 25, I will do 24. Number 24. And what are we supposed to do? A non-homogeneous differential equation with its complementary solution and a particular solution are given. Find use the initial conditions and find whatever you need to find. Okay, so the problem is y double prime minus 2y prime plus 2y is equal to 2x. We know y of 0 is 4, y prime at 0 is 8, and y sub c is c1 e to the x cosine x and plus c2 e to the x sine x, and y sub p is x plus 1. Isn't that lovely? So for our final answer, we would say that, well, not the final answer, before initial conditions, so we won't put that down. Okay, so y sub x is going to be c1 e to the x cosine x plus c2 e to the x sine x plus x plus 1. Yes, that's lovely. Y at 0. Okay, cosine of 0 is 1, is going to be C1, plus 1 is going to equal what? Going to equal 4. Clearly implying that C1 is equal to 3. Okay, well, that's good. Now we're going to take y prime x. Okay, so, and we're going to put a 3 in here for C1 as we do it. 3 e to the x cosine x minus 3 e to the x sine x plus c2 e to the x sine x plus c2 e to the x cosine x plus 1. Okay, so we've taken that derivative and we find y at, is it 0? What is the initial condition? Y at 0 is 8. So y at 0 is going to be 8. And I put a 0 in there. That's a 1. That's a 1. This is 3. The sign is 0. It goes away. Over here I have the sign of 0 is that goes away. Plus C2 plus 1, which implies C2 is equal to 4. Okay, C2 is equal to 4. So final answer, y of x is equal to 3 e to the x cosine x plus 4 e to the x sine x plus x plus 1. And we need to check it. So alright, well, we'll just do what it is. Y at 0 is supposed to be 4. Is y at 0 supposed to be 4? It's supposed to be 4. It is 4. Check. Okay. Y prime of x 3 e to the x cosine x minus 3 e to the x sine x plus 4 e to the x sine x plus 4 e to the x cosine x plus 1. Y prime at 0 is supposed to be 8. Okay, there's 4. That's a 0. That's 3. 3, that's a 0. That's a 0. That's a 4. That's a 1 is equal to 8. Check. It works. Y double prime x is equal to 3 e to the x cosine x minus 3 e to the x sine x minus 3 e to the x sine x minus 3 e to the x cosine x plus 4 e to the x sine x plus 4 e to the x cosine x plus 4 e to the x, no, it's, yeah, cosine x, no, yeah, cosine x, minus 4 e to the x sine x, and the 1 goes away. Alright, so I've got one of these guys, and I got minus 2 of that guy, and I have 2 of these guys, and when I get done, I'm supposed to have x, supposed to have 2x. I'm supposed to have 2x. Okay, here we go. I see 6 of those guys, minus 6. So these two guys go away. I see that guy and this guy going away. I see a 2x. I see the 1's going away. I see a 2x. Now, how about these other guys? I've got 6. I have 6 sine, and I have minus 6 sine. Minus 6 sine, minus 6 sine. These cosine terms go away. I've got minus 8 cosine, and I got plus 8 cosine, and those minus terms go away, and the only thing I have is 2x, and it checks. Isn't that lovely? And with that, we are done with section 3.2.